Welcome to This Explainer. Today we're taking a fascinating look at the very foundation of scientific discovery. Have you ever actually wondered how psychologists prove definitively that one thing causes another? Like, how do they know for sure that a specific teaching method works, or what a drug precisely does to our behavior? Okay, let's dive into this and explore exactly how psychological experiments are constructed from the ground up, tearing the method down piece by piece like a complex machine.
Here is our roadmap for today. We're going to hit the basic experimental method, variables, the power of controls, a couple of distinct experimental designs, the absolute importance of replication, and finally, the limitations of the method itself.
All right, starting right off with Section 1, the basic experimental method and formulating hypotheses.
At the very heart of any experiment, you have a core moving part. We call it the variable. Basically, it's just an event or a condition that can take on different values. And ideally, it's something we can measure quantitatively. Now, since psychology is essentially the science of behavior, researchers are specifically hunting for variables that change how a human or an animal acts.
Moving right along to Section 2, variables, specifically focusing on cause and effect.
In any good experiment, we have to strictly separate the cause from the effect. The independent variable, well, that's our cause. It's the specific condition the experimenter directly manipulates. Think of, say, giving someone meditation training or enriching a kid's environment with special books. The dependent variable is the effect, the behavior we actually measure at the end, like a change in their tennis swing or a higher test score. Now, what's really interesting about this slide is how we visually map all of this out. Conventionally, we put the cause, the independent variable, on the horizontal x-axis, also known as the abscissa, and the effect goes on the vertical y-axis, the ordinate. It lets us see, at a single glance, exactly how the measured behavior depends on what we tweaked.
Which brings us to Section 3, the power of controls, and keeping those conditions perfectly stable.
Take a second to really soak in this powerful quote. It is literally true that an experiment is no better than its controls. Honestly, if unknown factors are shifting around in the background while you're trying to test your independent variable, it completely ruins the study. Spotting those hidden defects in an experiment's controls is a true mark of scientific sophistication. It's how you cut through the noise, whether you're reading a dense journal article or just watching some flashy scientific claim on a TV commercial. So, how do researchers actually do this? Well, our first big strategy is using control groups. Picture this classic setup: a blindfolded line drawing task. Subjects feel a block of wood with one hand, then try to draw lines of that exact same length with their other hand. The experimental group gets our independent variable, verbal feedback when they get close. The control group? Absolutely zero feedback. But here's the catch. To know for sure the feedback caused any improvement, those two groups have to be matched perfectly. You can't have one group full of artists and the other full of, well, people who can't draw a straight line. To equalize all those extraneous factors, researchers either meticulously match the subjects on intelligence, age, and handedness, or they just assign them completely at random, hoping the differences balance out by chance.
All right, Section 4, 2 experimental designs, looking specifically at the within-subjects method.
Instead of wrangling two totally separate groups of subjects, researchers sometimes use a within-subjects design. Basically, subjects serve as their own controls, and this brilliantly illustrates that concept. In this study, hungry rats were trained to press a lever for food. Researchers tracked their baseline rate for 15 minutes, no drugs, just normal behavior. Then they introduced the independent variable, varying doses of a drug called neurotensin, plotted right there on the x-axis. By comparing that original normal baseline to the responses after the drug, every single rat acted as its own control group. It's incredibly precise because you're testing the exact same subject in both scenarios.
To really lock this down, researchers use what's called the ABA within subjects design. Think of it chronologically. Step 1, condition A. Establish that normal baseline behavior. Step 2, condition B. Introduce your independent variable and measure any changes. But step 3 is the true kicker. They go back to condition A by completely removing the independent variable. If that variable was the true cause of the change, the behavior should bounce right back to the original baseline. Now, obviously, this doesn't work for everything. Actually, scratch that. It literally can't work for permanent changes. If your variable is a new way to teach kids to read, you can't exactly unteach them to get back to a non-reading baseline. For long-lasting stuff like that, you just have to stick to those separate control groups we talked about earlier.
Let's hit Section 5, the importance of replication and repeating experiments.
So what happens after the experiment is wrapped up? Well, a single successful study is definitely not enough to establish a scientific fact. It needs checkability. I absolutely love that term. Basically, replication. Can other scientists repeat it over and over under the exact same conditions? If a dramatic finding is unrepeatable, there is no way it becomes part of the fabric of science. It's just like basic chemistry. If you burn hydrogen to combine it with oxygen, you get water. Anyone with the proper equipment can do it, and it's been replicated millions of times. In psychology, if we claim reciting information aids memory, we have to be able to replicate that, under the proper conditions, to prove its accuracy beyond all reasonable doubt.
Finally, Section 6, limitations of the method, because, it's not perfect.
Despite being the absolute gold standard for gathering information, the experimental method definitely has its flaws. First, it obviously can't be used if it's dangerous for the subjects. Second, lab settings can be highly artificial. Psychologists constantly struggle with this. Does a conclusion from a sterile lab actually apply to natural, messy situations in the real world? They have to constantly strive for generality. And third, the method itself can sometimes inadvertently interfere with the exact behavior it's trying to measure.
To show you what I mean by that last limitation, let me ask you a slightly counterintuitive question based on a real experimental setup on fatigue. Does pulling an all-nighter, 24 hours of total sleeplessness, actually improve your ability to do complex tasks?
A psychologist actually tested this. They took baseline measurements, kept people awake for 24 hours, and tested them again. And they improved. So the crucial point is, absolutely not. The answer is that motivation completely overshadowed the fatigue. Being in a laboratory, being watched by scientists, it introduced an entirely new, uncontrolled variable. The subjects were suddenly so motivated to perform well that it completely masked their exhaustion. It's literal proof that people in an experiment might not act the way they normally would on an average day.
Which leaves us with this final thought. If the experimental method can inadvertently change the very behavior it tries to measure, if a simple laboratory setting can make an exhausted person suddenly crush a test, how can we ever blindly trust a single scientific claim? Understanding the true anatomy of an experiment means realizing that science isn't just a list of facts. It's a continuous, relentless process of controlling hidden variables, demanding replication, and applying a really healthy dose of skepticism. So, the next time you see a bold scientific claim, ask yourself, what were their controls and what exactly was their independent variable? Thank you so much for joining me on this explainer, and keep questioning everything.